Hello and welcome to the Harvard Radcliffe Institute. My name is Claudia Rizzini. I'm the Executive Director of the Fellowship Program. The Institute is one of the world's leading centers for interdisciplinary exploration. We bring students, scholars, artists, and practitioners together to pursue curiosity-driven research, expand human understanding, and grapple with questions that demand insights from across disciplines. You can be a part of this vibrant community by attending public programs such as this one, visiting virtual exhibitions, or pursuing the special collections held at the Schlesinger Library. To learn more, you can visit radcliffe.harvard.edu and sign up to receive more information on news and events. We'll begin the program with a presentation by Elena Glassman. After the presentation, the speaker will respond to questions from the audience. Please use the Q&A feature on Zoom to submit your questions at any time throughout the program. We ask that you keep your questions brief to allow us to address as many as possible in the time that we have together. It is my pleasure to introduce Harvard Radcliffe Institute Fellow Elena L. Glassman. Professor Glassman is the Stanley A. Marks and William H. Marks Assistant Professor at the Harvard Radcliffe Institute and an Assistant Professor of Computer Science at the Harvard John A. Paulson School of Engineering and Applied Sciences. She has been teaching at Harvard since 2019. Professor Glassman's research specializes in human-computer interaction. She designs, builds, and evaluates systems for understanding and interacting with population-level structure and trends in large code and data corpora. In addition, she leads a research group with the goal of expanding human intelligence with computation. At Radcliffe, Professor Glassman is working on a project entitled Bidirectional Human-Computer Communication. This project concentrates on formalizing and generalizing a novel type of information visualization that allows for humans insight and intent formation about semi-structured data and, where applicable, the communication of that intent to a computer. This type of information visualization has been responsible for the success of Professor Glassman's past programming relating interfaces, and she proposes to expand it to new areas such as privacy policies, news articles, electronic health records, and scientific abstracts. The aim is to aid individuals and experts alike in various disciplines to observe formerly unrecognizable patterns and distributions over alternative choices that were previously excessively time-consuming to examine. Professor Glassman's father is an electrical engineer who fostered her passion for problem-solving with science from a young age. In high school, she went on to win the 2003 Intel Foundation Young Scientist Award, which is awarded to the top 3 science fair projects at the International Science and Engineering Fair. Professor Glassman earned her bachelor degree, PhD, and master's degree from the Department of Electrical Engineering and Computer Science at MIT. She has received fellowships from the Berkeley Institute of Data Science, the National Defense Science and Engineering Graduate Fellowship Program, and the National Science Foundation Graduate Research Fellowship Program. Professor Glassman's work has appeared in numerous media outlets such as CNN, the New York Times, and Wired. And now it is my pleasure to give the virtual floor to Elena Glassman.
Thank you for that very kind introduction. And I also want to acknowledge that while I can see the staff here, this is a challenging talk format, and I wish I could see you all, my fellow Radcliffe Fellows and all the guests joining from potentially around the world. I cannot see you. I can't see you not understanding or look confused. All these signals that I'll be talking about in the context of communicating with computers that I do all this research to support with better interfaces are sadly absent from this medium of communicating with you, my fellow humans, which I care about just as much. So I'll do my best to explain these ideas I'm currently developing and will continue to develop here at Radcliffe. And I welcome people reaching out to follow up about these ideas, as they are very much an act of current progress. This is some of the first times that I'll be sharing some of these thoughts with you today. So it's very exciting for me. Okay. So here's us, that cartoon on the left, and our computers represented here by a terrible cartoon of an integrated circuit, but it could be your laptop, your phone, your robot in the future. And As an expert in human-computer interaction, I can look at the interaction between these two entities in many different ways. But right now, I want to focus on a particular kind of conversation that we have with our computers that I think we take for granted. It's the one where we tell them what we want. So I'm going to blow up that conversation to the size of the room, our virtual room perhaps, so that the details that we aren't consciously aware of become visible. And I won't show you all those details at once. I'm going to use 5 vignettes to iteratively build up the subtleties that you may not have noticed before. In doing this, I hope that first you see your relationship with computers that surround us a little differently. Second, that you better appreciate the potential impact of answering the questions I'm trying to ask this year at Radcliffe, and also that you might get an extraordinarily brief review of some of my prior related work that it will inform my process of answering these questions this year. So now, when I tell you that this kind of conversation with our computers is taken for granted, I mean that I think most of us probably think of our relationship with computers to be pretty straightforward, right? I give command, computer executes. And the computer here, well, if this were true, if it were this simple, using computers wouldn't be so routinely frustrating. Let me illustrate that with some examples. So the first complication is that we don't always know what we want. In this first vignette, I'm thinking of a colleague at MGH, he's a physician and a researcher. He focuses on depression. He has access to thousands of patients' medical records at his hospital. Represented here is a pile of files, but in reality, it's probably just a bunch of files on a hard drive somewhere. And he wants to discover subpopulations of patients with the same disease that respond differently to treatment, so he can better learn about the disease and better personalize patient treatment in the future. He can write commands to retrieve all the records that fit some criteria he specifies, but he's not sure what criteria would retrieve a medically interesting subpopulation of patients in that pile. There's plenty of patterns, but only some of them are meaningful to him. If you were at Liebish's private talk at Radcliffe yesterday, she has a very similar research aim. She doesn't yet know what healthy even means in her context. She's not quite sure yet what truly distinguishes healthy microbiomes from diseased microbiomes, aside from the fact that some folks have terrible symptoms. So that formation of intent is the first piece we're going to add onto our framework here, our originally oversimplified framework. I have to come up with an intent, and it's not always easy. So, well, I'll add that it's not to say that without intent, computers are useless. Intent, I am saying, is an often under considered aspect of this interaction, and we should consider it explicitly and design interactions that help humans form and refine that intent as they gain a better understanding of what they want, what data they have, and what the computer is doing to that data or what it's capable of doing to that data. Okay, so on to our next vignette. It's from Keynote, a little bit meta here. Keynote has this really cool feature that allows me to put an object in one place on one slide and then in a new place in the next slide. And if I invoke the right command, Keynote will smoothly animate it for me when I transition between slides. It's really neat. Unfortunately, I have trouble remembering what that command is called, so it's difficult to search for. And it's also not visible in the animate panel, except when certain preconditions are met. And I cannot often remember what those are. So I have to rediscover how to use this function almost every time. It's really cool. It's called Magic Move. I highly recommend it. But I describe this because I know exactly what I want, but I cannot tell the computer until I figure out how. So I'm re-highlighting that command, that existing link in our diagram here in red to indicate that, like, hey, this is not trivial always. Now, there are user interface design failures here that I won't go into that make Magic Move harder than it needs to be to use. We could make it better. But at least this is a really simple and maybe relatable example, and it only gets harder when we're trying to express to a computer what to do in a less well-defined environment than simply moving an object from one part of a screen to another. So now let's illustrate the next set of complications we're going to add to this with Excel. So I've opened a spreadsheet. And in this case, the spreadsheet contains a long list of hockey players, but the data itself is not important. So I've set its opacity too low to be readable and hopefully not distracting. I know what I want. I've decided that I want a new column that has the player's first initial, their last name, of, and then their hometown. And then thanks to Google, because yes, computer scientists use Google to figure out what programming commands they should use as well, I figure out how to write a Excel formula that might populate this next column. Now I've cleared the first two hurdles that we just talked about, forming an intent and expressing it as a command for the computer to carry out on my behalf. However, I haven't written an Excel formula in a really long time, so I'm not quite sure yet that this will do what I intend. So let's find out. All right, so Excel executes the formula in all the rows. Oops. And I need to now manually check that it did what I want. This was my best attempt to translate my intent into a command, but until I see that it actually did what I want, it's hard to feel confident that it's right. Not only that, but checking over the results of the execution can bring up some additional interaction steps that you might not have considered before. For example, maybe I made a typo in my formula that I pick out, or maybe I misunderstood what left of D5-1 does, or the ampersand. Those are two very different failures. So if I made a typo, I could just fix the command. But if I made a conceptual mistake in my understanding of how the machine works, how it responds to commands, well, now I have to update my mental model of the machine as well. That might be part of this loop. And hopefully I've learned from that and don't make the same mistake the next time. There might be rows in addition with data I didn't anticipate, like someone with two first names, that might make me update my conceptual model of the data that the formula has to work on. So, and as I update my mental model of the data, that might even change what intent I think is the right intent. So, and even if I correctly translated my initial intent into a command, and I didn't see any unanticipated rows of data, I might still look at the result of my correctly executed intention and realize, oh no, that's not what I wanted. I want something else. So things don't have to go wrong for you to revise your intent and restart the whole loop all over again. Not just like restart from scratch, but this is this iterative cyclical process of sense making, really. So no matter what happens, each time I see the results of my command, I check its effects, I revise my understanding. I can go through each of these steps. Now, okay, so far we've gone from this really straightforward relationship with our computer to this. And so you might ask, are we done? Have we expanded it to the size of the room such that all the additional subtleties are included? And I would say not quite. I want to add one more layer here. And it's a really important layer, especially relevant today, because there's a lot of commercially available AI systems now that you get to interact with. So let me clarify why AI would come into this when. Okay, so in the Excel formula case, I wrote an Excel formula, and if there was any part of this that was not compilable, the computer didn't know what it meant, doesn't execute, maybe gives you an error, right? But there's another way of giving commands, which are partial specifications. So they might be like, what's the weather on Friday? This is not executable as it's written. There has to be some interpretation on the part of the computer. Another one that I hope I can say in the future to my Roomba, bad robot. We're not there yet, but essentially what this requires as we go from a complete specification to a partial specification from the user is this inference step, right? And that's kind of, once the inference step is there, we've gone from human computer communication to human AI communication. So let's see, I think that's almost our final piece. Let's do a couple more vignettes now that there's an AI in the loop. Okay, so you might be surprised to know that you don't need to leave Excel to illustrate this extra layer, this inference that the computer does. Though I swear we'll stop talking about spreadsheets soon. They just happen to be a really familiar environment that's still complex enough to illustrate a lot of these subtleties. So imagine now that I could not be bothered to look up how to write an Excel formula that corresponds to my intent. So I'm not doing that anymore. I know that there's this cool new AI-based Excel feature called Flash Fill. All I have to do is type in what I want after the first row. So again, Megan Augusta becomes M period Augusta of Ruthven. This is a partial specification of what I want in the form of a input-output example. Now I invoke flash fill, and using the heuristics and ranking functions and algorithms that Excel's designers have programmed in that we're going to collectively call inference, Excel has to guess what formula best replicates what I want on all the rows. And I haven't even told the computer what I want on all the rows. I only told it about the first one. So it's hopefully going to make an intelligent guess. So same as before, the only way I know if it gets right is by manually checking the results. Let's see what they are. Okay. So it's kind of hard to look at them all at a glance, especially if this were a long spreadsheet, but with existing tools and interfaces, which I hope to improve upon this year, all I've got is my unaided eyes. And fun fact, this is the same data as before, but since I didn't explicitly spell out that it should take the first character of the first name field, it decided that when a player had a compound first name, that it would take the full first name and abbreviate the second. And actually did this twice. I didn't even realize when I gave that initial example that there were compound first names in this data set. Also, I'll just point out that there are some characters in that place name that I didn't even realize were valid characters, but that shows my ignorance of the French. So, you know, this is part, so if this is not what I wanted, I'd have to notice that it did this, which is not trivial, given that some unanticipated complexity may be very infrequent. And in a really long spreadsheet, it might occur first on the 999th row. So, you know, obviously, you may not care exactly about how I abbreviate the first name of a hockey player, but it also could be, you know, the OCR results of a bank statement. There are ways in which we can change the stakes such that you would care about finding that. When I do notice choices that it made that don't match my current intent, because of course that intent may continuously be revised, I have to manually correct its output in the corresponding row so it can recompute the most likely Excel formula that represents the intent that I've partially specified with the examples I've given so far. So now you could ask, why are you going through the data yourself? If it's got 999 rows or 9,999 rows, you can't look at much more than the first few pages. Why not have the computer, your computer scientist after all, inspect its work for you and let you know when it's uncertain? And my answer to that, maybe I'll come around someday, but for now, I'm going to be stubborn and say, hold on, inference algorithms can be confidently wrong, and I've only given it a partial specification. Only I know whether it's doing what I want, and what I want is completely unobservable to the computer until, you know, we have much more invasive brain-computer interfaces. So by looking at what it does on the data I have, I may revise what I want, and none of those steps the computer can do for me. So for now, I'm thinking about how do I expand, speed up, scale up human inspection of the data and what the computer did to it. Now, you could also ask, why not look at the inferred formula? Well, inferred formulas can be atrociously hard to read. This formula is not one that was synthesized on our behalf by Microsoft, because they won't even show us what the formula was that made this output. But it just is here to give you an example of, depending on how a formula is written, it may exactly match what you wanted on the data you have and still be more complicated than it needs to be. It may not generalize properly to additional rows that aren't there that you didn't expect. And also, even if it's not more complicated than it has to be, they don't have human readable variable names because they're written by computers. And so, you know, there's a great quote from either Knuth or Abelson that goes, programs must be written for people to read and only incidentally for machines to execute. And right now, computers are getting increasingly good at writing executable programs, like the one that was generated for us, but they are not yet, they're still terrible at writing programs that humans can read and understand. So for now, we're left with just looking at the effect of the program on the data to reveal the contents of the program for now. So, all right, so let's update our framework with our second to last addition here, when possible, and that's not always, show inferred comments. Show inferred commands. All right. Okay, so we're going to look at two digital assistants real quick. Their differences will highlight the role of interfaces, and then we'll have wrapped up this new frame of thinking about communicating with computers. So in this fourth vignette, this is the screenless mini Google Home that I have at home. And I frequently ask it to cancel a timer. And sometimes I figure out that it misheard me right away because it immediately does something unexpected, like, okay, playing Child in Time by Deep Purple. When that happens, I can catch it real fast. And I can say, no, cancel the timer, right? And then, you know, I might not know whether or not it correctly canceled the timer. It says I canceled the timer, but I have found that because this is screenless and I have no awareness of its internal state, sometimes there are multiple timers running because I like to use the timer a lot. And so later the timer goes off and I'm like, what the hell, right? You know? So in this case, there were two inference steps that happened that were chained together. It has to correctly infer the words that I say, and then it has to correctly infer the meaning of the words. And so, you know, when you only have voice here, the discoverability of any errors is pretty poor. So I hope you'll be kind to your Google Home. It's struggling. One clarifying point here. You could say, well, you know, it blindly guessed it was wrong, right? Well, even if I asked a fellow human to cancel a timer when there were actually two timers running, they'd also have to guess, or they could ask a follow-up question like, well, which one? Because they have some amount of uncertainty. And I'll just note that both computers and humans can be confidently wrong in their interpretations. So we cannot perfectly rely on either to always clarify when a clarification is necessary. But still, it's a choice that we could give the machine in one more update to our framework here. So if uncertainty, where it will be a continuous open problem, I think, to calibrate its uncertainty correctly. If the uncertainty is too high, request a clarification. Or show multiple possible interpretations. So in our final vignette here, this is what it looks like to interact with a digital assistant that has a screen. And I use this example to illustrate to you why interface design, which is the type of research I do, is so important. It's such an important component of more useful and usable human AI communication. So when I speak with Siri like this with a screen, it sometimes misunderstands what I say, but at least I see what it thought I said. And I also see what it proposes to do on my behalf. And I am able to abort a proposed action that I don't want. And I'm also able to clarify what I spoke by some other means other than speaking, like typing, right? In case I have a heavy accent or I am in a loud room. So the addition of the screen and how that screen supports the interaction is hugely impactful for how many round trips it takes for me to clarify what I want and to confidently, correctly understand that the computer also got what I wanted and is acting on it as I want. Okay, so we have these three vignettes of where there's a complete specification. You could call that human-computer interaction. And then we have these additional three vignettes of where there's a partial specification. You could call that human AI communication. So that's where I make the distinction here where we're, you know, it's all computers, but AI is a buzzword and we only want to use it when it's truly applicable. And this is the final kind of, this is the size of the room, interaction possibilities, and each one of these arrows or steps, right, can represent a failure, not necessarily a failure like bad human, right, or but an opportunity to misunderstand, an opportunity where an interface designer can make things better. And so now I like to point out that most work in AI today focuses on these inference algorithms. And of course, you know, the better the inference algorithm, it gets you really, really far. We can't do the human AI communication without an AI. But I want to point out that the focus of my year is on all of this cognitive work that if we don't support the human in doing it causes unnecessary frustration and limits the potential of what we can do, augmented, having our intelligence and our abilities augmented by computers. So Now, so as an interface designer, I'll be focusing on those interfaces. And now in the remaining time that I have, I'll give you a little bit of a sense of some prior relevant work I have been a part of that will help you that'll give you a sense of how I might think about tackling these challenges. So before I thought about communicating with AI and helping humans do that, I thought about helping teachers communicate with their students. I was actually a teaching assistant or a teaching fellow in a very large engineering class. And while I didn't have 1,000 students like Professor De Niro at UC Berkeley in his large programming class, I certainly still felt pretty overwhelmed, right? And like, what am I going to talk about in class tomorrow, right? Students just sent me, thousands of submissions. What did my students write? What bugs are they struggling with? These are all things that I would want to know before I formed an intent to give a lecture or before I chose examples to try and clarify a concept students are struggling with. So I spent my entire PhD kind of publishing in that realm. And what came back again and again that worked in that context was to leverage the structure of the corpus of code, the programs in this case, written by students or written by the community at large. Once I started thinking beyond the classroom and say, hey, we're all really lifelong learners. Just because I'm programming in an open source environment doesn't mean I'm not interested in how other people solve this particular problem as well that I might learn from. So it's to leverage the structure. Prior to my work in this space, people were coming up with structure, but it wasn't necessarily usable structure. So here you can see each one of these nodes represents a program, and they are kind of connected to each other by some edit distance. And you click on them if you could. I don't believe this was ever clickable. It's more of a Jackson Pollock painting. If you wanted to do that, it would be incredibly difficult to form some big picture view of what your students are doing and how they're failing, because even as I click into these things, it's not clear to me why some things are closer than others. Really, it's a very domain specific version of the memory game, right? And I can only have a couple of these programs ever open at once. Instead, the idea was to abstract away the variation I didn't care about as much and try to align examples from diverse environments written by different people that shared commonalities that could reveal the structure in the mess. So I have a pile of code, and I would design or potentially infer an abstraction that captures what I've expressed as a human as the thing I care about. And then that would reveal this population level view of how people, in this case, called that particular API file input stream. So over here, you can see we found by looking at all these different examples, this is the head of a long distribution of different ways people instantiated the arguments to that function call. Okay, but we can do, show, and then after they might call some functions on those arguments. They might check something is true before they call it. And here, I didn't even realize there was essentially a 2-to-1 ratio out in the wild, people using this API, where they invoked it twice as often on a file object than a file name. But if I have a file name, I want to look at the distribution. I could interact and look just at the choices, the distribution of choices for people who also were operating with a file name. So obviously, file input stream is not what we care about here. It's the methods that allow us to interrogate how other people, out of this pile code, how other people were making design choices, common and uncommon ones that I could maybe learn from and leverage myself. Of course, this is kind of like a mask almost on top of the underlying code here that was annotated and pre-processed to fit in, kind of almost like registering against each other in this meta view. So I did that kind of method in the classroom. I call it a data landscape because you kind of think of it as, in the classroom, I'd have students working on one way of approaching the problem, and I'd have a different set of students working on the other. And often, because these solutions were so complex, if you didn't have something help see the landscape of, oh, here's how those are different, and here's this distribution between them, and also more unusual, terrible, and also awesome, very infrequent ways of solving it. I anecdotally, other people told me on the staff that they would They're like, wait, there's 2 ways to solve this? I was telling everyone who didn't do it that way, I told them they were wrong. Like, no, that's why we need to understand that landscape. So I created overcode and FUBAS to show in the large Python programming classroom, the distribution of design choices that people made in structuring their program and the variable names they chose. Even variable names are actually hugely important design choices. And so this answered for a given programming assignment, what do my hundreds or thousands of student solutions look like for those the teacher in that original vignette, and also enabled a more informed teacher who could strategically pick examples from these interfaces to illustrate their points to the students, and give better, have feedback that they wrote propagated automatically to more students. I'll just point out with B, right, strategically picking examples for these from these interfaces to illustrate their points is just as relevant when we're communicating with a computer as it was when we were communicating with a bunch of students. So that's one of the connections I'm drawing on. We generalize this to outside the classroom with Exemplar, which I showed you previously, and also ExampleNet, which generalize this idea. Okay, you're going to write your neural network for the first time, right? What's the distribution over sequences of layers that other people before me, writing a neural network for analyzing images, used? What's the distribution over hyperparameter values for this particular layer? If you don't, speaking of having no intent initially, right, this would help you inform, like, oh, okay, usually it's between 10 and 20, right? I'm certainly not going to initialize it at 1,000. It kind of helps you. It answered, how did previous programmers use function X in the wild, and enabled more correct, comprehensive understandings of the function in question, and also helped people make more informed choices and fewer design mistakes and omissions, right? If you see a pile of 100 examples and one person has that extra check that makes sure you don't, have this particular kind of error, most other people forgot it. But if you can see that deduplicated, the redundancies deduplicated, so that you can see the variations in context, you might notice that, oh yeah, that one person who I wouldn't have been able to randomly probably see. That's a great choice. I'm gonna do that too. My code will be safer. And in the final parallel, but even more obviously relevant to my work on human AI communication this year, is my work on novel interactive communication interfaces for requesting programs from examples. So Reggae and interpretable program synthesis. I'll go the least detail into them, but I'll tell you that these interfaces for very much like Excel, but slightly different. This is for regular expressions acting not on a spreadsheet, but hypothetical future data. And we added new novel interface affordances that allowed the human to constrain the AI to generalize examples as the user intended. So if I give an example of a phone number, I may want you to synthesize a regular expression that matches that a phone number, not a phone number that starts with 2 and 5, right? Those are just examples of possible digits, right? And so I can actually annotate, yes, the plus sign in front of it, you have to have that. But these are instances of a more general class. By making that explicit, I cut down on the types of inference leaps that the AI could get wrong. We also allowed people to see how the AI's interpretation of their intent would play out on new, possibly unanticipated inputs. So they don't have to try and come up with that themselves. That's a tricky task. We allowed them to select additional interface generated examples from B to further specify their intent. Like, oh, okay, here, I can add that to my spec. Thanks for suggesting it. And allowed people to see distinguishing examples between the AI's multiple interpretations of their intent. So like we mentioned before, the AI could ask, hey, I'm not sure. Is this what you meant? But it could also say, I can't distinguish, given what you've told me, between these 3 options. And showing distinguishing examples can help the user looking at these 3 options for the first time, refine what they want and pick. Finally, it helped, these interface affordances helped better help the AI thought process be a little more explicit and allowed people to reach in and say, oh, you're looking over there, but I can tell you're not going to find anything over there. go look here. So that, in summary, created quicker, more successful conversations with the AI, where people got the program they wanted more quickly, which is exactly what we want. With these vignettes, I'm focusing on big piles of data where intent is not clear, and where the piles might actually help me come up with examples to specify what I want to the computer, and also to reflect back to me in context what the computer is doing. And instead of focusing on code, I'm open to other types of semi-structured complex data, like text. And maybe not necessarily within a particular community, but in whatever data set that's coherent, that has some common semantic meaning. Maybe all the leases in Boston, because when signing a lease, you might want to know, is this an outlier? Why is it an outlier? So this is the focus of my work. Even if that part went by too fast, the connection to my prior research, I hope you came away with a new appreciation for this conversation that we're constantly having with computers, whether or not they've got an AI behind them. When you're frustrated, blame the interface, not yourself. Finally, I'd just like to thank the funders who have made this work so far possible, the NSF, the Radcliffe Institute, of course, front and center here, and SEAS, Harvard SEAS, where where my students sit. So if you're interested in any of the details of these particular projects, I'm happy to answer questions here over email, and also all the preprints are available at that URL, glassmanlab.seas.harvard.edu. So I'll take your questions.
Wonderful. Thank you so much, Elena. This was great. And there are indeed quite a few questions. So let's go to the first one, which says, are your data landscapes topological? As in, is it useful to think about the flow of information through a data landscape?
This is why I love the Radcliffe Institute, because I've never thought of that before. I've often thought about it as kind of a static, a picture in time, right? Here's where your current solution or your particular microbiome in your case is sitting within this landscape, this kind of where kind of the histogram almost is creating the mountains. Certainly, if you're thinking about the evolution, say, of the microbiome, specifically over time, to show its movement through the landscape would entirely, like, you could start, I mean, you could create it. That would be a legit thing to do. I think that could be, I hope that would be helpful.
Great. The next question is, can you talk about which aspects of human cognition you think are the most tractable to your work? To work with.
Right. Okay. So I'm so glad that you brought up aspects of human cognition, because I think about that a lot. I'm not a cognitive scientist, but I read voraciously from that field to try and find theories of how humans form conceptual models, right, of how the world works, such that we can create interfaces that better inform, that work with their natural inference processes to make correct inferences about how the AI is operating on their behalf. So I think about how humans make inferences from consistency across examples and variation across examples. And that's, I think, best described in variation theory, and also maybe a little bit less so, but still in analogical transfer theory, right? So by seeing many examples, like many different microbiomes and all these different ways in which they're consistent and all these different ways in which they are different, the variation within a class can help me understand, oh, that's not a critical aspect to a healthy biome, right? But this is always present. And as long as I have a sufficient amount of data such that I'm not missing out on the population in another continent, which has a totally different microbiome, then I can make accurate generalizations about what are critical features of what I care about and what aren't critical features. So I hope that speaks to that question about aspects of human cognition I think about.
Yeah, I think it does. Let's see, how might your model of human AI interaction and partial specification inform how we think about social communication more broadly, in which two minds are working together to figure out what they want from and give to one another?
I think really, you can, just as I was thinking about this before, where the computer was instead a classroom of students, and you wanted to clarify a concept by picking examples that varied in certain ways and were consistent in others. I think you can take exactly what we talked about today and replace the computer back with a human, individual or a population. So yeah, I mean, whenever we try to communicate something, I think about like basically a basic statement in English, right? I might use a word that you don't know, right? We operate in language without pointing at things, being like door, right? Because we assume we have a common mapping of words to meanings. However, we don't always have that common mapping. Maybe it's hard sometimes to detect a mismapping. And then when I use a word you don't know, well, now I have to kind of fall back on examples, right? If you didn't know what a mouse was, or no, if you didn't know what a computer was, I'd be like, well, here's my laptop, that's a computer. Here's my iPad, that's a computer. Here's my, here's my phone, right? I hope through these examples that, what's consistent and I might be able to kind of on the fly develop a conceptual model of what that abstract word means. Yeah, I'd love to talk more about that. I think it's basically nothing would change.
Right. The next question is, how does the domain affect the understanding of intent? For example, NASA engineers versus end users, Google researchers.
Okay. So how does the domain affect the understanding of intent? Certainly, one way that it could affect things, right? One of the reasons why flash fill and Excel, at least, I mean, I don't have too much insight into it's proprietary, but I think initially when I knew the folks working on it, they said there was a lot of tuning, right? It was highly tuned to like the typical things people asked for in Excel, so that it usually got it right the first try. Because I thought that if people had to provide additional examples, they would be less and less enamored with the feature. And so, when you are in different domains, and maybe your probability distribution in inference over what the person might mean would be kind of swayed one way or another. It's really hard to get those priors in advance. So I like to focus less on trying to guess accurately and more on trying to support the human in expressing themselves clearly, so that those priors matter less and less. There's less guesswork for the computer.
The next question is, do you think that different cultures, genders, and so on struggle with coding, in particular in the sense that most of the coders in the past were male?
Well, I know, I believe Margaret Burnett has talked a lot about the impact of gender on programming, being in a programming community, the code that you write. And I don't know that work as much as I would like. So I defer to her on the gender question, but certainly something I could pull up is that some people are coding in, a lot of code is written with English, right? And if you're not a native English speaker, now not only you're trying to understand code that's not, so super easily readable, but all these contextual clues that we give each other, right? When I hand you this program that's incidentally for a computer to execute, but also for you to read, right? There's all these contextual clues. And if you don't pick up on those contextual clues because you're not part of my community, or you don't even speak the same language primarily, it's lost. It's much harder to reconstruct meaning.
Yeah, here's a fascinating question, actually. That's the next one. You talk about interaction between humans and computers as if you could presume that there would be on one side something completely human, and on the other a computer. But what about how much influence of computers we already carry inside us, and on our way of thinking and seeing?
Yeah. Oh, so the most basic way this shows up is actually in the guidance that that I give my students in my interface design class, that they be consistent with the interfaces that their intended users typically use, right? It's funny how, we think of usability, we often teach of usability as like, well, here are the things, if you have this, this, and this, it's usable, right? But in reality, there's a huge dominating aspect of what are the expectations, what are all the previous computer interfaces that the person you are designing for used to use that informs their guesses about where to find things. As I get older and older relative to my students, they will design stuff that reflects the interfaces they are comfortable with. And I'm like, how do I use this, right? And like, I don't give them an F because I can't use it. I just appreciate that we are shaped, our expectations are shaped by our previous interactions with computers 100%. Just the other way, I acknowledged, right, that flash fill is a product of human designers making executive decisions about what the architecture of that feature is going to be, how it works. And so I am, in a certain sense, interacting with that human, even though the human is now long gone from the interaction. I'm interacting with the trail of their decisions. So I appreciate that point.
The next question is, I'm curious as to how big data models might augment AI as a way of teaching machines to recognize and interpret messages. I'm thinking about the difference, for example, between Google Translate and earlier AI translation softwares.
Yeah, so I mean, I guess like I have been very cautious about using big language models, in part because I want to see what it is that they've been trained on, right? Because I know that they will essentially regurgitate in slightly creative ways, depending on how you define creative, what they've seen before. Whereas, with Exemplar, right, instead of saying, hey, I trained my big data model on how everyone else used this API, why don't you use it to spit out some examples, right? Instead, I'm like, here are all the examples. You can see the examples, right? I've abstracted away enough of the details that I hope you don't care about so that you can see the pile. So with that caveat of not being as comfortable with big data models, certainly, as I think about what role they could play, they are increasingly good, but still confidently wrong and subject to all these kinds of kind of accidents of different proportions of what happened to be in their training set. And I think focusing not so much on the big data model itself, but how we can be minimally impacted by the composition of its training data and very quickly overwhelm its output with the intent that we are expressing as clearly as we can with the interfaces I'm trying to build. Yeah. I hope that gives some clarity.
The next question says, Paul Dorish famously suggested human-computer interaction as a field takes embodiment into design considerations. Can you discuss how physical interaction features may influence your design choices in regards to cognition and inference?
Yeah, so variation theory, which I've mostly been leaning on to think about how humans form concepts from the data that they see, is very much about simultaneously showing kind of analogous but varying examples, so that, like, instead of kind of incrementally correcting your understanding, you leap to a more robust, generalized understanding of the phenomenon you're interested in. And in physical embodiment, that's kind of not yet possible. Like, I can't simultaneously experience moving the robot this way and moving it that way, and seeing the difference in how it responds to that feedback of, stay out of my space. And so I think that's a really, that is a threshold that I'm not quite sure yet how to cross, given the techniques I've used so far. But it is something I'm actively thinking about. And it may mean that that you interleave periods of embodiment with periods of interacting with a representation of how that movement is happening, but on screen, so you can see kind of time aligned across multiple rollouts of a robot's policy. And I'll just point out, this is actually somewhat similar to a PhD thesis that came out of robotics lab, Rodney Brooks's lab at CSAIL before he went off and started various robotics companies, where essentially the PhD student had a robot interact with the world. It can only interact so much. In every interaction, it could fall over, it could hurt itself. And then, every so often it would go to sleep and then would play out rollouts of what it had learned in a simulated world. And every single time it went out into the world, it risked bodily injury, but it also created a better mental model of the world. And every time it slept, much like rats dream of going through mazes, after a day of going through mazes, it would dream about how it would move in the world the next day.
Mm. Fascinating, endlessly fascinating. The next question is, can you speak to non-screen centric interfaces for preschool age children and enhancing foundational literacy through data-driven recommendations and experiences? Can data help guide read aloud experiences and conversation across languages and cultures?
Wow. Okay, so we're in the world of non-screen interfaces. Let's see. So certainly the one connection that I see here with what I know already is that kids can be very quick to pick up not only screen-based interfaces, but talking to Alexa, right? Sometimes to hilariously bad effect, and that they're ordering things you didn't want. Interfaces that are not screen-based, while they are much more difficult to discover, right? How do you know that you can ask, read me a story, right? Or read me a different story? There's no visibility of what the system is or isn't capable of. But if you are willing to try, and I think a lot of, I don't yet have a preschooler, but if I imagine that they are very willing to try and ask all sorts of things of the machine, that could be an interesting interaction. I'm not quite sure yet from the question what data what role that would play in the interaction. So I'll leave that unanswered so that I don't put forward an idea that I later regret.
And that's totally fine. The next question asks, can you please say a few more words about how to influence models to overcome the content, for example, biases of their training sets?
So I just preface this by saying I am uncomfortable with using large language models. There's papers, I believe one famous one that is title escapes me, but many have come out about kind of the dangers of these methods. And that's why I focused more on kind of here's the data you have, help you form some intent, but there's no big data model operating here. I guess the only place where kind of biases could show up is like, okay, if all the other Excel users wanted that function and I wanted this function and I was using a big data model in the back end, I guess the trick is to make sure that the way that you're collecting the user's intent, or that the way that you're allowing the user to express their intent, is able to effectively rule out that big mass of alternative ways of doing it. Right? You don't want the system to say, are you sure you don't want it the way that everyone else is doing it? And you're like, no, as long as you allow the user to very quickly eliminate the things that are coming in because of like the system's own biases towards large amount of data it already has, then that's my current hope for incorporating but mitigating some of the bad effects. But if we can avoid it altogether, I think for the moment, I'm still more comfortable with that.
Right. The next question is, what is the riskiest risk in your work?
Right. So riskiest risk is a term that I learned from Hachi Zhang and the Delta Lab at Northwestern. I would say there that I feel very grateful that I was able to identify these kind of common conceptual frameworks that allowed me to see hundreds of API usage examples for this, at once, right? To kind of have the hallelujah moment, oh my goodness, like I see it, right? From this pile, there is, I have this new insight. And so, there's always that question of like, how far can I push this before there's no more hallelujah moment at the end of the design process. And I think, the current boundaries are making sure that, if you've got a pile of documents or a pile of code, right, if there's nothing that makes them semantically related enough to each other, they have to be tightly enough semantically related. It was all from the same programming assignment in the same class, or maybe the same programming assignment in different classes, that's okay. Maybe they're all using the same library, but once you get too far, I think the noise overwhelms the signal. And so, that's, I think, being very careful about how the domains in which I expand so that I can clarify the repeatedly useful techniques, the menagerie of techniques that you might be able to use in the future if you want to design one of these interfaces for data that you have.
Mm-hmm. And the next question is, how do you imagine your research impacting clinical research that it's based on electronic medical record analysis? Can you give us an example of a research project in which your work would make a difference?
Sure. Well, there's I actually don't know if it's public yet. There's a workshop paper that I was a co-author on with Finali Doshi here and Tini Zhang, who was my postdoc. He was the lead author of many of the papers that I showed here today. He's now a CS professor at Purdue, that he led, where we looked at trajectories of events that happen to someone who is diagnosed with depression in a given hospital system. And so if you align all the patients' records, the events that happen to them at the point of that diagnosis, the hope is that given that we're looking at just people suffering from depression, and that we are aligning them on kind of abstracting away the individual time at which that diagnosis happens, through the alignment, we were trying to show how could we kind of show the emergent patterns of ways in which someone came into that diagnosis and ways in which people interacted with the medical community after that diagnosis, either switching between medications and not finding something that was working for them, or recovering and going off. Now the data is incredibly messy, and that's still a work in progress. But I think that if we can, again, finding the right abstractions that and finding the right things to abstract away, such that the details that are relevant to the doctor are present, so that they can start to form their own hypotheses, possible intents that then can inform the queries that they write in their SQL database to actually go about and say, yeah, this is a medically significant subpopulation we should focus on.
Mm-hmm. And the last question is one that I think it's kind of inevitable in this kind of talks. And it says, in your opinion, how far away are we from strong AI, an AI that rivals human intelligence in terms of ability, function, and perhaps self-awareness?
So I am not afraid of the singularity. That's what this is referring to. And I don't mean to laugh at the question. I mean, it's certainly, I think at this point, I am repeatedly confronted with the stupidity of the things that I make, the limitations that I think we are very, very far away from an AI that rivals human contextual awareness, right? That's one of the things, why am I talking about the human and the machine talking to each other if the computer could eventually go without the human? Without the human, it has no purpose of what to do. It's the human that's driving, coming up with what to do, and figuring out how they want help doing it.
Absolutely. Excellent. Thank you, Elena, for your fascinating presentation and perspective. I also want to thank you, the audience, for the terrific questions. I hope you will be able to join us for other Radcliffe virtual programs. You can find out about future programs and watch videos of past events at radcliffe.harvard.edu. Thank you again for joining us today and have a good rest of the day. Bye.
Thank you, everyone.